Alright folks, we are here to wrap up Module 7 with a hopefully relatively pain-free piece. We're going to be talking about kind of one aspect of research that is very meaningful but that doesn't get covered too much in this course, what we call effect sizes, and then talk a little bit about where hypothesis testing as an approach to statistics is going. Important note, hypothesis testing, we emphasize it heavily. It is not the only way to get answers to our questions. It's just the most popular one. So again, there's a lot of ongoing debate about the best way to approach our research questions. So starting at the beginning though, this idea called effect size is something that's become increasingly prominent over the last few decades in statistics. So here's the premise of effect size. At the end of a hypothesis test, you're either going to reject the null or you're not. There's no other nuance to it. It's significant results or significant results, period. But here's the thing. We want to separate sometimes our significant results into just how influential they are. Basically, how big the effect is, essentially. So even really small effects where our two population means are actually pretty close together, they can still be statistically significant, especially if you measured a lot of people. Remember, you measure lots and lots of people, the standard error gets really, really small, and your population means no longer need to be very far apart. My wife works in health psychology, and she deals with data sets that are tens of thousands of people, sometimes once in a while hundreds of thousands. Here's the thing. Basically, any effect, any difference, any correlation in a data set that size is almost certainly going to be significant just because, again, there's so many people there that the standard error is tiny. So it's very, very easy to reject the null sometimes with relatively small differences between populations when you measure a bunch of people. So again, remember that logic of the sampling distribution. The exact same gap in terms of the number of points between sample means is much more likely to be significant as you measure more and more people. So here's what effect size is designed to do. It's designed to add a little more nuance to a significant result to expand on just, is this improbable enough that we can reject the null, and say, how big is this effect? How much is say the IV changing people's DV scores by? So effect size is about magnitude. It's about size. It doesn't tell us whether or not it's significant based on probability. It tells us how big does it appear to be. So effect size is essentially how far apart two populations are. Generally in an experiment, we have one population represented by our control group. That's usually population 2. We have our experimental group represent another population, population 1. Effect size is how far apart are those two population means. The farther apart they are, the bigger the effect is. In an experiment, you'd say the more influential your IV was. So it's literally how big and important a significant effect is. If they're really far apart, you're going to get a big number. If they're pretty close, you're going to get a smaller number. Here's the formula for effect size. Don't worry about test problems with this formula or anything like that. We might talk about effect size on there, but you're not actually going to be calculating effect sizes. But this is something you'll probably look at a bit if you get into graduate school. But here's a very popular measure of effect size, Cohen's d. Notice it's just the difference between the two population means you're comparing divided by the standard deviation. Very similar to a z-score formula, right? There are some rules of thumb. A small effect size is anything bigger than 1/5 of a standard deviation apart. That doesn't seem like much. Medium is half a standard deviation apart. Large is 0.8. So here's our for future service on this. We'll talk about effect size once in a while for the remainder of these modules, but not much, really not much at all. But it is actually a pretty important part, especially of more advanced statistical procedures. So effect size gives us that added dimension, not just as a result significant, but how big does it appear to be, which oftentimes means how meaningful is it or how influential is our IV. Some courses, especially in graduate school, some journals may require you to report effect size measures. There are lots of different ones, but that one you just saw the formula for, it's called Cohen's d. It's by far the most widely used, but there are lots of different options. If you wind up in grad school, you're probably going to be working pretty heavily with effect sizes, but we won't see much of it in these remaining modules. So again, significance testing is kind of the gold standard for research, but it is not perfect, especially that fact that significance tests result in those binary decisions where if you're a tick on this side of the line, you're rejecting the null hypothesis and your paper gets published and you get attention and all that good stuff. If you're a tick on that side of the line, your result is non-significant. No one will really pay attention to your research or publish it or do anything that provides some kind of perverse incentives when there's only two possible outcomes and they can be very, very close together. Basically, as statisticians have kind of dug into the use of significance testing, especially in fields like psychology, they found first that people aren't accounting enough for that alpha inflation. Remember, alpha is the probability of a type 1 error. And alpha inflation basically says, all right, if you run more and more tests, eventually you're going to get these false positives. You're going to get significant results that aren't real. With enough tests, it can start to become pretty close to certain that you will have at least one type 1 error, one false positive. A lot of researchers didn't account for that. There's also been an issue with what's called p-hacking. P-hacking involves taking a situation where you run your analyses, and gosh, your results are pretty close to that 0.05 line, but they're not across the line. What do we do in that case? Well, people started getting real creative with what they started doing to those data sets. They weren't necessarily making up data, but they might find a reason to delete some scores that would push it across the line or come up with a different way of scoring the variable. Or sometimes they might start off with an alpha of 0.01, find the result, stop short of that, and say, well, our alpha is now 0.05, which is unethical as well. You're supposed to set your alpha in advance to running your study, exactly so you don't do that sort of thing. So they've caught a lot of people doing p-hacking. There's some really neat ways they can look for evidence of it involving probability. But a lot of people were just doing maybe gray area kind of stuff, dubious stuff to their data sets to push them across that line and suddenly magically make them significant. Some researchers, this is less common, but some researchers will even conclude that failing to reject the null hypothesis is proof that the null hypothesis is accurate. It is not. Failing to reject the null just means your results are inconclusive. You don't have enough evidence to reject the null. It does not tell you that the null is true. When we accept it, it just means inconclusive results. So here's the thing. This isn't like, computer software where it's going to be obsolete in 3 years. Hypothesis testing is going to keep being the most common framework. But if you stay in the field, if you stay engaged in research, you will almost certainly start to see alternative techniques become a little more prominent. But change is slow. This is still a very convenient and useful framework. So it is what is going to be used in scientific research for at least the near to medium future. All right, I'm sure you're all very excited to be doing statistical research by now. So overall for the module, be familiar with why we do hypothesis testing. Certainly be familiar with the steps. Again, you are guaranteed to be asked about to run hypothesis tests. You're guaranteed to be asked some conceptual questions about them too. We're going to learn for the rest of the semester various ways of testing hypotheses for different types of data sets. Be familiar with those decision errors. They're not as important as running the test overall, but they're plenty important in their own right. They, again, revolve around that idea of uncertainty in our findings. Sometimes we will make the wrong decision. And again, be aware of or familiar with how that connects with other course concepts, especially with things like alpha and power. And effect size, again, adds an extra dimension to our significant results, how big the result is, not just how likely it is. All right, that's the end. There are some more practice problems if you haven't looked at them already. Get lots of repetitions in working those 5 steps and keeping track of what you need at each point, and importantly, why, because you'll be asked some questions on that as well. And again, you will have that. You also will have your third graded quiz after this as well.